Now let's deal with an interesting problem about popular culture. I am a fan of Running Man, so maybe some of you are also fans of Running Man, and I especially found a problem from a previous episode that you might want to solve for it. In the Running Man episode 216, Lee Kwang-soo tried to pass through this bridge, as shown in the figure. His right hand here, touching this bridge, exerts a distributed load of 400 Newton per meter. So his hand is here, okay? Assume his shoes and knees exerts 70 Newton and 500 Newton concentrated load on this bridge respectively. So his shoes here has a load of 70 Newtons, while his knee gives a 500 Newton load onto the bridge. Sketch the shear stress and moment diagram of this bridge from point A to B. Assume it is a simple beam. Well, firstly, we try to find the reactions at the two supports A and B. By considering the force and moment equilibrium, you can find PA equals to 382.95, PB equals to 367.05. Next, we need to consider the loading condition in each segment. Say, since it is a concentrated load, distributed load, right? So we try to divide the section into different segments such that we can analyze the load condition in it. Because in different position X, sometimes some forces is removed. Sometimes you have to neglect some forces from your analysis. Consider the first section for X from 0 to 600 millimeters. On this section, it's rather easy. We take the moment at this end. The moment is given by PA times X. The shear force is given by PA. For this section, it is rather easy to analyze. For 600 to 1000, the shear force is given by PA minus 70. The shear force is given by PA minus 70 newtons, while the moment is given by PAX minus 70 times X minus 600. So here is 600 and this is the X. The 70 Newton force will provide an arm of X minus 600, and for the force PA, it will generate an arm of X. So consequently, you can rewrite the moment and the shear force equation in those forms. Then you can find the moment at this position and this position as well. For 1000 to 1250 millimeters, which is this segment, so it is X. PA has an arm of X with respect to this end. The 70 Newton force has an arm of X minus 600, while the 500 Newton force will have an arm of X minus 1000. So you can find the moment equation like this. For shear force, it is just the force equilibrium. Eventually, you can find the shear force and the moment equation in this form. Actually, no matter how you find moment and the shear force, from left section or right section as you like, as long as you keep the correct sign convention, then you will get the correct answer. Now let's consider X from 1250 millimeters to 1700 millimeters. We adopt two methods to find the moment. One is the left section and another one is the right section. For the left section, the sign convention is like this. The shear force can be easily found by using this formula. But notice that in the original problem, here it is given by 400 Newton per meter. So this unit can be converted to millimeter one, which is 0.4 Newton per millimeter. So you can find the shear force, which is PA minus 70 minus 500 minus 0.4 times the length of this distributed load. Simplifying it, get 312.95 minus 0.4 x newtons. For moment, it is also not easy to compute. First, the PA still generate an arm of X. The 70 Newton force will generate an arm of x minus 600. The 500 Newton force will generate an arm of x minus 1000. For the distributed load, the moment is a little bit complicated to compute, but it should be fine. First, the length of the distributed load is given by x minus 1250, and as we know, the moment center of this distributed load is located in the middle of it. Therefore, the arm generated will be 1/2 of x minus 1250. Then you can find the moment like this, and then you simplify it to get this result. However, it could be faster if we can consider the right section. So consider the right section and label the rest of the forces on this beam. Now you only have one distributed load, and there was no 70 Newton and 500 Newton load acting on it. Now the length of the distributed load is given by 700 minus x, and the arm generated by the distributed load is given by 1700 minus x divided by 2. At the same time, PB will generate a moment with arm 2200 minus x. Therefore, by combining all those informations, we can find the shear force and the moment equation by using the right section. So for the shear force, it is just the distributed load minus PB, which is 312.95 minus 0.4x. The result is exactly the same to the method 1. Similarly, for the moment, we also adopt the right section to compute it, and we expand this result. And this result is exactly the same to what we found by considering the left section. As you can see, considering the right section can simplify the problem a lot. So notice that you should always bear in mind with the sign convention. For the left section, the shear force is downward. For the right hand side, it is upward. So bear in mind with that. And similarly, for the last section, from 1700 mm to 2200 mm, from the left section, you can find it is very complicated computation. While if we just consider the right section, it will give you the same result. So there is no reason that we consider the left one instead of the right one. So always bear in mind that you should always keep the correct sign convention for the left and the right sections. So bear in mind, it is very important. Finally, we combine all our known results into consideration, the Vx for different sections, as well as the moment Mx for different sections. Also, we compute some boundary conditions, like what is the moment and the shear force at 600, 1000, 2050, 1700 and 2200. We compute all those boundary conditions such that we can sketch the shear force and the moment diagram. So the shear force and moment diagram is sketched in this way. Just now we deal with the shear and the bending moment diagram of this beam. Now let's concentrate on the impact of the sectional properties on the material performance. First, we will derive the centroid of an isosceles trapezoidal cross-section mathematically. The upper base A, lower base is B, and the height is h. The upper base is smaller than the lower base, so like this. Besides, we will consider to make this bridge by using the concrete, knowing that concrete has very different yield stress for tensile and compressive stresses. The tensile yield stress is 5 million pascals. The compressive yield stress is 40 million pascals. If we ignore the shear force inside it, let's find the minimum section modulus required under a safety factor of 2.5 and the minimum cross-sectional area required for a square section. The reason why I require 2.5 as the safety factor is that I don't know whether Kim Chong-gu will pass through this bridge just by stepping on it. Besides, due to the constraint of program budget, a PD, program director, suggests to make the cross-section trapezoidal to save the cost of the bridge. So they want to have the minimum usage of the material such that they can save money for building the bridge. Design a cross-section such that the use of material is minimized for a safety factor of 2.5. You want to design the bridge such that the minimum cross-sectional area is attained. You are also required to think of it. What other design considerations should be involved? Firstly, for isosceles trapezoid, it is significant that the average value of x is lying in the middle. For the average of y, we need to first construct the x prime and y prime coordinate systems, such that we can find the first moment of inertia of this cross-section. First of all, let's find the moment of inertia of this triangular shape. For this triangle, dA is the region bounded by the line y equals to 0 as well as y equals to 2h divided by b minus a times x. So it is notated like this. It is the range of y, the lower and the upper limits of y, which is bounded by two lines. Besides, it is also significant that x is ranging from 0 to b minus a divided by 2. Consequently, you do the integration like this, and then you take out the constant, as well as further integrate x squared dx by using this upper and the lower limits. Then the integration shows that the first moment of inertia of this triangular shape is given by h squared times b minus a divided by 12. Finally, you consider the area of this tiny triangle. You found that the altitude of the centroid is given by h divided by 3. That means the average value of y for the triangular shape is h divided by 3. Then we combine the result of first moment of inertia of the triangle with the result of first moment of inertia of the rectangle. We assembly all those components together to get a complete trapezoid. The first moment of inertia of this trapezoid is given by the first moment of inertia of the triangle plus the first moment of inertia of the rectangular region, which is 2 times the average value of y of the triangle times the area of the triangle plus the average value of y of the rectangle times the area of the rectangle. Then you substitute all the stuff into it and do the simplification to get the first moment of inertia of the trapezoid, which is given by h squared times b plus 2a divided by 6. You also know the area of the trapezoid is given by h times a plus b divided by 2. Therefore, the centroid of the trapezoidal cross-section can be found by dividing the first moment of inertia by its area. It is given by h times 2a plus b divided by 3 times a plus b. Then we can find the centroid of the trapezoidal shape. Next, let's talk about the design consideration of the material, concrete. The yield stress for tensile and the compressive are very different. Therefore, we need to take the section modulus for tensile and compressive sides into consideration. From part A, we know that the maximum moment is 355 Nm, and if we are taking the safety factor of 2.5, then consider the tensile region. The allowable stress is given by the yield stress divided by the safety factor, which is 5 MPa divided by 2.5 equals to 2 MPa. Therefore, you are going to find the section modulus by using those two conditions. By substituting the values into those two conditions, you will find the section modulus of the tensile side, which is negative 177500 mm3. So what is the moment of inertia of a square cross-section? It is given by I equals to d to the power 4 divided by 12, where d is the side length of the square. For this beam, since the maximum moment is acting somewhere on this beam, that means the beam will be deflected like this. Therefore, tensile side will be below the neutral axis, while compressive side is above the neutral axis. At the outmost point of the tensile side, y equals to minus d divided by 2. We solve for this equation, that is, we put the moment of inertia as well as the outmost value of y into the section modulus equation, and we solve for d. Therefore, d equals to 102.1 mm and the area is 10429 mm squared. In part C, we discussed the possibility of building this bridge by using a square cross-section. Now let's try to build this bridge by using trapezoidal cross-section. Due to the constraint of program budget, a PhD suggests to make this bridge trapezoidal to save the cost of the bridge. We can save the money by cutting some material down such that we can reduce the cost of the concrete. That is, we want to minimize our cross-section. To do this, first we consider the moment of inertia I of the trapezoidal region. The answer is this. because the steps of derivation is too complicated, so it is left to you as an exercise in the practice problem set. Next, consider the section modulus required for both compressive and tensile sides. Just now we found the section modulus required for the tensile side. So now let's find the section modulus of the compressive side. Notice that the yield stress of the compressive side is 40 MPa. And by using 40 MPa divided by 2.5, you will get the allowable stress, which is 16 MPa. Then the section modulus can be found to be 350 Nm divided by 16. Remember, since we're talking about the compressive side, that means the allowable stress as compressive, it is negative, so we put a negative sign here. Consequently, we will get the section modulus, which is 22187.5 mm3, which is positive. So now for compressive region, we have the section modulus should be greater than this value, while the tensile region, the section modulus should be less than this value. That is, we want the section modulus to have higher magnitude. That is, if we set the section modulus to be greater than this value, then that means the section modulus should have a magnitude which is greater than this. Similarly, for the negative section modulus, if I say I want this section modulus to be less than a negative number, that means I want this section modulus to have a magnitude which is greater than this one. This is how we can strengthen the cross-section properties. Now, we have to satisfy both conditions. We also want to minimize the area of the cross-section. Besides, according to this diagram, we know that HC plus HT equals to H. That is, the height of the compressive region plus the height of the tensile region equals to the height of the entire trapezoid. Since the critical section modulus required in tensile and the compressive regions are related by the 8 times relationship, to minimize the use of the material, suppose for this trapezoid it satisfies HC equals to 8HT, that is, the height of the compressive region is 8 times to that of the tensile region. However, it is impossible because the lowest centroid allowed for the trapezoid should be greater than h over 3. It is impossible to make the centroid to be lower than h over 3. That means if you say the centroid is located at h divided by 9, then I will say it is definitely impossible for a trapezoidal cross-section. Unless you change the shape of the cross-section, then it is impossible to do that. So we try to adopt the lowest value of the average value of y, lowest value of the altitude of the centroid, which is h divided by 3 for our further analysis. When we take the centroid to be h divided by 3, the trapezoid will become a triangle in this case. Then a equals to 0, and we do a lot of cancellations. 0, 0, 0. And finally, you will get Ixx simplified to be h cubed b divided by 36. For compressive region, the section modulus expressions can also be simplified, as well as the tensile region. Also, we know that a equals to ha plus b divided by 2, but in this time, a is 0. Therefore, it will become hb divided by 2. Let's consider the tensile region. Then we have this inequality, because the statement from the tensile region, which is this one, is stronger than that of the compressive region. We simplified our problem a lot, and finally we draw a conclusion that we are trying to minimize the area, which is given by hb divided by 2, by using the condition h squared b is greater than 2.13 times 10 to the power 6 mm3. However, it seems that we can make h to be infinitely large and make b tends to 0, such that the area of the cross-section tends to 0. So it is just the pure mathematics that we try to analyze how to minimize the area by using a given condition. We know h can be very large while b can be very small. So if we make h to be very large, then the area will tend to 0. It will be very, very small, but it is not a reasonable design. One reason is that if we only take the cross-sectional area into the consideration, that is, we try to make the area very small, then you will get a cross-section looks like this. You're crazy? As an engineer, you design such a cross-section? Still remember that how Yi Guangsu passed through this bridge? He is just riding on this bridge. If you give him such a bridge, then yeah, tragedy happens, right? The sharp tip of the triangular cross-section will immediately kill him. Yeah, and somehow, even though you say, okay, you are able to ride on it, but somehow it could have another issue, which is the strength of the material in other directions, because when he is passing through the bridge, there could be some literal load. Not only the 1D loading, but also the literal load will occur. For example, in this direction, somehow caused by the friction, right? So in case there is such a load occur, then how can you ensure the safety with such a thin cross-section? Then it is another issue that you need to address. In another word, the minimal value of A, which is the minimal value of the upper base, would be necessary for a reasonable design. So in our practice problem set, there is a problem which is modified from this problem, and there will be a value of A given, and you can try that out.